This is number 1 from the AP FRQ review for particle motion with calculator. So number 1 says a particle moves along the x-axis with the velocity given by v of t, and we can use and plug this in our calculator. We want to make sure that our calculator is in radian mode. So I have it entered in here. 10 sine of 0.4 x squared divided by x squared minus x plus 3. Even though you may see different variables to plug in the calculator, you're always going to be using x in your calculator. Okay. The particle is at position x equals -5 at time t equals 0. So we know the position at t equals 0 is -5. Find the acceleration of the particle at time t equals 3. So acceleration is related to velocity by a way of derivative. So if I evaluate the derivative of velocity at 3, then the result is acceleration. So we can do that. I have y1 storing the information from velocity function. So if I want to find acceleration at 3, I don't have to go through the trouble of finding the derivative by hand. I just make the calculator do that for us. So if we do math 8, okay, that will take us to n derivative feature, and we can just do d over dx of the function, which is the velocity function. I'm going to call that function rather than typing everything in again. It's stored under y1. So if I do vars, scroll over to y vars there, function y1, and I want to evaluate the derivative of velocity at t equals 3. So this will give me my acceleration. So my acceleration, I'm going to round to 3 decimal places, -2.118. Okay, part B, find the position of the particle at time t equals 3. Well, we know the position of the particle at time equals 0. We just have to bridge the gap between 0 and 3. So we can use this formula here where anytime I'm looking for a position, I can start with a given or initial position. Initial doesn't always have to be 0. It's just whatever the problem provides for us. So the initial position in this case is 0, x of 0, which is -5, plus displacement. So here's the formula in variable form here. X of b is equal to x of a plus the displacement from a to b integral, the definite integral from a to b of v of t dt. So if I want to find the position at t equals 3, I can start at x of 0 plus the definite integral displacement of velocity from 0 to 3. Enter this in the calculator. You can do math 9 from 0 to 3. Again, rather than typing everything in, I'm going to rely on vars y vars variable function y1, which holds my velocity function dx. And this will give me a displacement of 3.239. I've traveled a distance, well, this particle traveled a distance of 3.2397 in this time interval. And if I take that and if I combine it with the initial starting position, then if he starts at -5 and moves 3.23 units to the right, he's going to end up at -1.760, and that is the final location, final position. Part C, evaluate the definite integral from 0 to 3.5 v of t dt, okay, which we did, 3.73. 3.5. So we're going to have to reevaluate from 0 to 3.5. So displacement is 2.843. Okay, 2.844, and evaluate the definite integral of the absolute value of v of t. So this is referring to distance. So we can get to distance if you do math 9 from 0 to 3.5. Now, if we want to have that absolute value notation, we're going to go to math number, so math number ABS, and we can now put in that velocity function. So the total distance traveled is 3.737. Okay. So if we're talking about the same time interval, then the total distance is going to be at least as large as displacement, but many times it's going to be larger, especially if that particle changes direction. So the distinction here is the definite interval of v of t is the displacement of the particle in the time interval from 0 to 3.5, and then the absolute value of v of t, dt, is going to be total distance traveled by the particle from 0 to 3.5. Okay, now part D, we have a second particle introduced. So this second particle is given by x sub 2. At what time are the two particles moving with the same velocity? Well, we have velocity information from the first particle. So let's get to the velocity equation for the second particle so we can just match apples to apples. So the derivative of t squared minus t is going to be 2t minus 1 if I do power rule. So now we just want to figure out when do these two particles have the same velocity, so I can set the two velocity functions equal to each other. So I have the velocity that's given to us at the beginning of the problem, and then I also have the velocity that we found from the second particle, and we set them equal to each other. This will be difficult to solve by hand, so why don't we do this? Why don't we just subtract this 2t minus 1 over to the left side, and now that we have everything on one side with 0 on the other, let's just use our calculator to graph this expression and see where this graph actually crosses the x-axis. So if we graph this equation and look for the x-intercept, then we have the t-value that will make this a true statement. So I'm going to go back to my y1, which holds my initial velocity function. My y2 holds my new velocity function, 2t minus 1. And I'm just going to graph the first velocity minus the second velocity. Rather than putting everything on the same line, I'm just going to call it y1 minus y2, first velocity minus second velocity. I can unhighlight the equal sign, which just means that we can choose not to graph these functions. Hit enter at the equal sign, and as long as we don't have the equal sign highlighted, then the calculator is only going to graph the one that we highlight. So if we do zoom 6, takes us to a 10 by 10 window. We just want to see where is this graph going to cross the x-axis. So right now that's tough to see. We can do second trace, or we can do zoom box. I'm going to see if I can zoom in on that x-intercept there, because right now it's a little bit blurry. So it looks like it's going to cross somewhere between 1 and 2. To find that, make the calculator find that x-intercept for us, we can go to 0, second trace 0, hit enter. And my cursor, I'm going to choose a point to the left of the x-intercept, hit enter. Right bound, so I'm going to scroll to a point on the other side of the x-intercept, hit enter again. And now the calculator knows to look between these 2 points, hit enter a third time, and it'll find that x value, 1.57. So that means at time t equals 1.57, these two particles will achieve the same velocity. It's not asking for that velocity, we just have to know what time they are equivalent.